Alright guys, welcome back to the conference room. Let's finish the chapter 1 of the book with the little section on how things can go wrong. Let's do it. So basically this small video will show you why it was important for us to learn about security requirements, right? Why did cryptographers created these notions of security, this concept of security notions, security attack models, and things like that? This is why it's important. You will see why. So first of all, I'm going to define two ways in things where things can go wrong. Oh no, this is not asymmetric encryption anymore. This was the last video. Alright. How things go wrong. Alright, two ways things can go wrong mainly. One is due to a weak cipher, okay? Weak cipher. So the best example is Cipher cipher and Vigenère cipher and all of the encryption algorithms that were invented a little bit in the past that were broken. So weak ciphers can be broken with what we saw is cryptanalysis. So Cipher cipher can be cracked by trying all the possible shifts. And same with Vigenère. Now, another example of a weak cipher is the 2G. So I'm going to do example 2G, the 2G communications. Right? Now we have 4G, but before there used to be 2G, and 2G used an algorithm called A51. And that A51, this looks like an S. A51 was an algorithm that was broken by cryptanalysis. Now, what can I say? Breaking an encryption such as this one, which is a more modern, obviously was used for telecommunications, so it's a more modern informatics encryption algorithm. Breaking this wasn't easy. It took 10 years of intense work by many cryptography and security researchers. So it's not that it's easy to break ciphers. Like this cipher is not easy to break, but it took quite some while. And also it's the attack that breaks it. It's called time and memory trade-off. It has a time memory trade-off. That means that to break a ciphertext generated by this cipher, you'll need at least 1 terabyte of memory and days or weeks in advance to pre-compute what's called lookup tables. So you pre-compute some tables. I don't want to dig in the detail. Maybe you can Google this. I certainly will Google this tonight and find out a little bit more about it. But just know that this is a great example of a weak cipher, the book gives it, and broken by cryptanalysis. Now, another way, so this is simple. Weak ciphers, cryptanalysis will break them, right? Now, another example of how things can go wrong, you can have a cipher that is very strong, but you might have picked the wrong model, or you might have defined the models wrongly. Let's see. So wrong model can make things go wrong. And let's talk about this a little bit. So sometimes the cipher is secure, but the system that a system or an application that works with the cipher might be exploited for an attack. So let me see. Let's give a more concrete example. I'll give an example of what it was called a padding oracle attack, right? So let me see, I can structure this good. Okay, so in a padding oracle attack, let's take a very strong cipher, a cipher that will take a plain text, will take X amount of data. This is, let's say this is a string of data. A symmetric encryption algorithm that will take this piece of data, break it down in blocks of the same size. Break it down in blocks of the same size. Okay. And then XOR each one to doing XOR with each one to create a ciphertext, right? Now the cipher itself might be very strong, but what's problem is the system that checks the validity of a ciphertext before it's sent to the encryption. So we have the decryption, right? Where you have a key. Obviously the key is what the attacker is trying to find out, right? Here the attacker can listen to many ciphertext and plain text pairs, but doesn't know the key. So, and we get a plain text, right? So now, what I mean by wrong model is that there can be a system before here, another process. Let me see, I can call this. There can be another process, and in this specific example, padding check. So since the data, as I was showing before, the algorithm, the cipher breaks all the data in same pieces, what happens if the last piece is not of the same size of the other pieces of data? This is a plain text. What happens is that these, actually no, what happens is that the software, the application, will add padding so that these are all the same size, okay? They're all the same size. So adding padding is something that an application or a system can do to make sure that everything is the same, each block was the same size. And I think more in the future we'll do block ciphers. This is called a block cipher. And so back to us, we have a system that takes a ciphertext, right? And it does what it's called a padding check. If the padding check is successful, then the decryption will take place. If the padding check is unsuccessful, then we'll get an error. Okay, so now we have a situation where an attacker can send many variations of a ciphertext, right? Let me see. Actually, it doesn't check, especially for C. It checks the padding in the, okay, let me see, in the plain text, okay. Right. Perfect. So by manipulating the last byte of C, the system will check if the corresponding ciphertext is valid by checking the padding of the resulting P that comes out. And so, again, the gist of this is that the attacker, So the cipher itself is not weak, it's strong, because it's a block cipher that has, you know, the indistinguishability, you know, mutability, everything secure. But what's problem is that the system, the padding check system, becomes something that the attacker can interact with how many times he wants, and change and send different ciphers. And let's say we have a cipher of 1, 2, 3, 4, 5, 6 bytes. Then for each byte, it needs to only try all possible combinations for each byte. So it's basically 0 to 255, right? The values that can be here. So there's 256 possibilities to get the byte right, which is very little for a computer, right? So it will basically manipulate byte after byte and use this called as a padding oracle. The oracle will tell you error or will tell you correct. When the attacker finds that it's submitting a ciphertext with the correct, that returns the correct padding check, then he just needs to perform some XOR operations with that byte and the resulting plaintext, I believe, and basically it will find out the plaintext of that block. So the attacker will work block by block, because each block gets XORed with the next one and gets encrypted, etc., etc. And so by doing that byte by byte, it will guess all the bytes of the plaintext. So it will literally decrypt it will literally find out the key, because now he knows the cipher, the plaintext, it will find out the key of the encryption, which then it will allow him to break every secret that uses the same system. Now, let's make a comparison of why this attack is very effective. So let's say we have, not this a small amount of data, but we have a 128 what calculation did I make? So let's say we have a 128 byte or key to find out. The whole point that I'm trying to make is that classically, if we wanted to break by brute force, we'll have to try 2 to the 128 for a 128 bit key, I believe, or byte key. It will need to try all these combinations before finding the correct key. But with this attack, with this padding oracle attack, it will just need to use 256 for each byte, so for 128 slots. So it starts from the last one, we'll try 0 to 255 until there's no error coming back from the padding check, and then, you know, etc., etc. This for 128 times. Way faster. Fast. Slow. Okay? And this is the point. Again, the padding oracle attack, I wish I could explain the technicalities better, but it's a bit outside of the scope, but it's a great example of picking the wrong model. Why? Because the mistake wasn't to pick the wrong cipher. The cipher itself, it's secure, it's a block cipher, symmetric algorithm cipher, blah blah blah. But what's wrong is integrating in a system where there's a check or something else that the attackers can interact with. So it failed to recognize that an attack model that, you know, that the attackers can do to the system. And so this is how things can go wrong in cryptography, in encryption, in ciphers. And if you want to, and this concludes chapter 1, if you want more reading, the author suggests a paper called Probabilistic Encryption and How to Play Mental Poker Keeping Secrets All Partial Information by Goldwasser and Micali. Read more. So theory, the theory of encryption it will be the paper by Goldwasser and Micali. Paper. For physical attacks and cryptographic hardware, it's better to use, what does it point to? CHES conference. CHES. Okay, CHS conference material, and in general, for the latest research in crypto, eprint@iacr.org. There's crypto. We said eprint@iacr.org. Okay, so yep, that's it. This is for reading more, because the author says a lot of this was just chapter was just a broad introduction, and a lot of very cool topics obviously could not be included. The next chapter will deal with and talk about randomness. Okay, so I'm very excited to go on and understand the randomness with you guys. So yeah, that's it. I'll see you in the next video. Thank you for watching.